All right, second half of the trig integrals, they get a little more complicated when you have tan and secant. So I went over the rules in the intro video and obviously in class. So I wrote the identities that you need to do these up at the top. I also wrote two common integrals. There's one I haven't written that I'm about to write. So, again, why this works is because tangent and secant are in each other's derivatives, right? The derivative of tan is secant squared. The derivative of secant is secant tangent. Now, the one integral that I deliberately don't do until I reach this point is this one. So the trick is simple, though. You're going to rewrite tangent as sine over cosine. Now, I will have done this in class, but for the benefit of people who don't have me as their professor. So I always told you that when I taught you U substitution, I said to you, if you see a fraction, always pick the bottom to be the U. So the U in this case would be cosine. That means that du would be negative sine. So then when you make the replacement, now you're going to have a minus right there. Sine x dx, you're going to put for du. Cosine, you're going to put for u. And now you already know how to do this, right? The negative's still there. This is just ln u. But the u was cosine. So that gives you negative ln cosine. Now this is where it gets a little weird. There is a property of logarithms that said if you had a power here, you could always put that power in the front. This is what you did in pre-calculus when you did logarithms. So if I have that -1 there, I could actually take it and go put it up here and make that cos -1. This is why when all the books do the integral of tan, technically, it is negative ln cosine, but they don't write it that way. They move the negative up as a power of cosine, and then they flip that over and make it 1 over cosine. Right? That's what it means to have the -1 power. You flip it over, you take the reciprocal. 1 over cosine is secant. So this is the way that they write that integral. Now I'm putting parentheses. The books always incorrectly put absolute value there. It doesn't make sense. They always do it. So I don't do that. So that's the last one that I'll need because it does pop up during these integrals sometimes, not often. But now you know how to handle all of them. Except secant. It's really complicated to integrate that. You have to use parts or some weird trick that no human being knows. All right, so the first technique said very simply, if you see that secant is even, and in this first example, I have secant 4. So then you split that up. Now, you don't split it up this way because that's not going to help you, right? Your goal is to get a secant squared to be the du. So I'm going to have to split up secant 4 as secant 2, secant 2. You have to be very clever how you do these. Like I said, this is death for a lot of students because there's a lot of scenarios that pop up, and you have to understand why you're doing things, what you're doing. Now it looks strange. Like, what? I got 2 of them. Only one of them is going to be the du, right? This one here that I pulled off is going to be my du. This one has to get replaced with the identity. My u is going to be tangent, right? If you're going to pick secant squared, that means, as the du, that means that the u had to be tangent. So then you're going to go and replace secant squared with its identity, which is tangent squared plus 1. And again, this is so similar to with sines and cosines. It is more advanced because these derivatives are more advanced. But it's the same exact strategy. So you split it apart. That's my du. I'm still going to leave it there. Now I have everything in terms of tan. Now, here's where I cheat a little bit. Remember, I'm going to distribute tan 6 and tan 2. Remember, add the powers. I'm going to get tan 8. Over here, I'm not going to do that with secant because I'm not going to write s because it could be sine. You're going to get tan 6. And then I'm still going to have secant squared x dx. At any point, I don't even know where to put it. You're going to pick your u to be tan. So that means that the derivative of tan is secant squared. But again, this is what I want. My derivative of tan is right there. There's tan. I know at some point students will just do 1/9 T9, but you want to actually make the u substitution like you were supposed to. That is the point of this question. That's du. The only nice thing about these, when you were doing this with sines and cosines, if your u was cosine, then you ended up with a negative sign. and then you had to switch all of them. This doesn't happen here because there's no negatives. That's the reason they picked tan and secant instead of cos and cot, because those involve the negatives, right? The derivative of cot is negative cos squared, and the derivative, same thing, derivative of cos is negative cos cot. So that negative signs just add a level of complexity that doesn't need to be there. And then you integrate it. So now I am going to do the cheat just to save time, right? I know this is 1/9 U9, blah, 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 right? 1/7 U7, and then you put it back. So I'll just jump to the punchline here. You're going to get 1/9 tan to the 9th plus, my plus looks horrible, plus 1/7 tan 7, and then don't forget the plus C. At this point, the techniques are so hard, I don't even care anymore. Plus C is not there, whatever. So, right, again, even did not matter what tan was. This could be tan 7, this could be tan 5, this could be even or odd. If this is even, this doesn't matter at all. So if this is even, you split it up with 2 and 2. You always need a secant squared. If that had been secant 6, you would have done 2, 2, 2. All right, no worries. And then you just start replacing the identities, distribute, and then make the U substitution. Okay, so they will get a little bit harder, so you do other ones. Okay, so number two, they're both odd. Tangent's odd, secant's odd. So if you were to try to pull apart a squared here, right? Let's say you did secant 5 and then secant 2. And say, oh, I can make this my du, but the problem is the secant 5. Even if you try splitting that up, not happening, right? I mean, it's secant 5 is odd, so you're never going to make it match this identity. You could do 2, 2, and then you have an odd one out. So that doesn't work. So that's why in this case, you're going to start looking for this. This one's a lot more complicated. You have to be very careful, and I'm going to write it really carefully. I'm going to take tan 3, and I'm going to split it up as tan 2 and tan 1, right? I'm going to pull off 1 from the tangent dude. And I'm going to do the same thing with the secant dude. I'm going to take that and make it secant 6, secant 1, right? So you have to do something really different when they're both odd. This is not the same, right? The sine and cosines were easier because the strategy was always the same. Odd one, split it up, and it didn't matter. But here, it matters, like how you split it up. You have to be smart about it. Now, I'm going to take the ones that I just did. Let's do it in red. I'm going to take those two, and I'm going to group them to the end, and I'm going to write it the way my antiderivative is. So I have tan squared. It's very tempting for me to just write t squared, because when I do them on my own, that's what I do. And then I have secant 6. And then at the end, I have secant tangent. Don't write tan secant. Write secant tangent, because that's the integral, right? That's the du. So if that's what I'm getting, then I know that my u, right? I guess I'll put it over here this time. My u is going to be secant. That means that my du is going to be secant tangent, right? Right there. I got to put my dx, or I'm imprecise, and I don't like to be imprecise. So, because it's like, well, which one do I replace? But this tells you what to replace. There's only one trig dude whose derivative is secant tangent, and that's secant. So, right, this is why I wrote them there. So I need to replace tan with secant, right? My u is going to be secant. So I have to replace tan squared with the identity. Thank God it's not that bad. So again, I'm going to use the top one this time. Tan squared is equal to secant squared minus 1. Right? These are the trig identities. And yes, I give these to my students. I see no reason not to give you these. I mean, you still have to do all this crap on your own. So giving them to you isn't super helpful. Now I'm going to distribute. Again, these get tight. They take a while to fit. So let's do red. Make it look all pretty. Secant 6, secant 2. Again, adding the exponents. It's not secant 12. Right? It's secant 8. And then over here, secant 6 times the negative 1. Just make sure you watch your sign. You're careful. Now, technically, it's supposed to be parentheses there. Now I can replace it all. This is right. This was the game. U, du. So where secant is, you put the u. And you see these problems get very redundant after a while. That du right there. And then again, you would get 1/9. It's almost the exact same answer as before, except that there's a minus here instead of a plus. So I'll jump just to the answer. You're gonna get 1/9, right? Add 1, divide, and it's secant this time. So it's secant to the 9th. Minus, and again, add 1 to the power, divide. So you get 1/7 secant 7th, and yes, plus c. Right? Add 1, divide. Add 1, divide. Or add 1, flip it and put it in the front. Whatever you like. That's what I do too. So again, more complicated when you see the two odds. You got to split apart a single tangent and a single secant so that you have the secant tangent to do the du. That's the whole trick when they're both odd. All right, so I'm going to see which one is next. I'll pick one to do. Okay, so even though they start to get a little redundant at this point until a certain scenario pops up, I'm going to just start this one. This one is tan 3 secant 1, right? There's no power, it's just secant. But that's odd, so they're both odd. So you would do the same strategy. Look, you already have a secant there. So this one just requires you to take the tan third, split it up as tan squared times tan x, right? Times secant x. I don't like it written like that because it's backwards. So I would do this, right? I'd write secant tan. And then you'd replace the tan squared with the identity, secant squared minus 1. And then remember, right? The u is going to be secant. I'm doing this one fast because I want to get to I just want to at least show you the setup of it. Right, so you just, here, there's nothing to split up. There's just one of them. So you just take off one of these dudes to hook up with the secant. So you have your secant tangent. And then the u is secant. There's the du. So the only reason I'm doing this is just to show you this part at the end. Here you would get the 1/3 u to the third, right? Add 1, divide. But here you have to make sure when you integrate 1 with respect to u, you get u. Now I know I encountered that with the sine and cosine ones, but I just wanted to make sure. And then you would finish this. I only wanted to just show you really quick how to split that one up. Okay, so you look at 6, it's tan squared. Again, there's no secant there. So you immediately start thinking, okay, what the hell am I supposed to do? There's nothing to split up. And there is nothing to split up. But it's actually quite simple. Because I gave you tan squared, if you just replace it with his trig identity, you get secant squared minus 1 dx. That's it. Right? I mean, look, I never do this, but you have to understand the rules work like this. I need a dx here. Right? We never do this. Like if I ask you to find the antiderivative of, something like that, you're technically splitting it up into 3 integrals, right? I mean, this is what you do. No one writes this. This is absolutely ludicrous. You just take the antiderivative of one thing at a time. But this is really what you're doing. But in this case, it actually helps you to really see what to do. You're integrating secant squared, and then you're integrating a -1. -1, right? See, -1. So, but you already know this integral. You know that antiderivative. It's just tan. Now, you have to be careful here. I did not do any u substitution. This is an x. The integral of 1 dx is x. Right? Don't believe me? The derivative of x is 1. And there's a negative. There it is. Right? Derivative of tan, secant squared. Derivative of -x, 1. It's that simple. All you had to do in that problem was just pop the trig identity in there. There's nothing to it. Now, the next one. All right, so the example that I'll talk about and not finish, really get upset, but when secant's even, split it apart. No problem, right? Make a secant squared pull off. When they're both odd, right? Tan's odd, secant's odd. You take 1 from each. That was like question number 2. Now, the question is what happens when secant is odd, but tangent is even. Now, you might want to, you say, oh, but I'm going to just split apart. You can just pull 1 from each. Just pull 1 from each. And then secant squared. And then you can take the secant tangent. The problem with this, you'll see, right? I have a secant tangent left over. That's got to be my du. And then you say, oh, but then you could replace this with tan, right? Secant squared is tan squared plus 1, but you can't do that. My u is not tangent. If my du is secant tangent, then that means my u is secant. That means that I would have to get rid of the tangent here. And there's just no way to do that. So same thing, if you try to split it up right? No matter how you approach this, no matter how you try to split it up, as soon as you have the tan and the tan, you're totally screwed because there's nothing to put there. Now you might also say, oh, but I could put secant squared there. You could put secant squared minus 1 there. But where does that get you? Because even after you do it, you get secant to the 5th minus secant to the 3rd dx. Where, and he's like, oh, u is secant. Where's the du? Where is secant tangent here? You can't just put u5, u3, and you don't have a du, so this doesn't work either. So what you have to do, unfortunately for you, would be to do this. You have to do this deal. This is brutally difficult. Now, in a previous problem, you have secant cube there, which also has to be done by parts. It's also it's a little simpler than this one, but it depends on you. Now, I mean, you don't have a lot of choices. You're either going to make the dv tan squared, or you're going to make the dv secant cubed. But this is the problem with what happens when secant is odd but tangent is even. You really get completely screwed over. There is not a nice way to do this. You have to use parts. You have to use identities. It's absolutely insane, and it would take me probably, because it's not as simple. Oh, you do integration by parts one time. You don't. This is a reason. If you ever see this, and if I'm not your professor and you're given this on a test, your professor completely screwed you over royally. Cannot do this. This integral is incredibly advanced and complicated, and it goes far beyond the scope of what you need to be able to integrate. So odd secant even tangent, if it's tan 3 secant 3, no problem, right? Pull off one of each, make the exchange. If secant's even, no problem. Split it up with a secant squared. The u is tangent. No, but here's a scenario where you run into a dead end. No matter which one you put here, it's going to be very complicated to do. We already did this one. The problem with this is that you have to do integration by parts on secant cubed. To be able to do that, you have to split that up as secant squared and secant. This would be the dv. This would be the u. This is dv because the v would be tan. So you have to do integration by parts within the integration by parts. It's fucking insane. So, good luck to you if your professor decides to give you that. I'm not going to do this to my students. So there you go.